lesson is looking at the derivatives of all the functions that we've done so far. What do you notice? All the ones over here on the left-hand side are all the ones that you guys have done the formal definition with. The blue are the ones from the actual lesson. The red are the ones from your homework, okay? So the first one was the do now for today. The derivative was 3x squared, okay? Looking at your notes from Tuesday's class, what was the derivative of x squared plus 1? From the notes. It was
Are we supposed to be writing this down?
You don't have to write this part down because this is kind of like a investigation type thing that I'm guiding you through. What about this one? X squared minus x plus 2. That was the last one from the notes.
2x minus 1.
We got 2x minus 1. Now all the ones from the red were from your homework. So look at your homework. You had to do the formal definition with 2x squared. What did you get for the derivative?
4x.
4x. What about 2x minus x squared? I think that was number 16b when you did the formal definition.
Which
16b.
Yeah. 2 minus 2x.
It was 2 minus 2x. This one here, this was number 19. You had to use the formal definition to find the following. What'd you guys get for number 19?
Negative 2x plus 5.
Negative 2x plus 5. This one here, this was number 20. You had to do in the 20A, you had to use the formal definition. What'd you get there? 6x. And then the very, very last one was 17b. Even though you had to find the gradient of the tangent 2y equals 1 over x, you still had to use the formal definition to do it. Who actually got this one?
I think I did.
What'd you get?
Is it negative 1 over x squared?
That was correct. Okay? Now, if you're like, oh man, yeah, I definitely do good on my homework. Well, here were your answers for those respective ones, okay? Not the full answer, because some of them you actually had to plug in. But what do you notice between the original and the derivative? What do you notice between the original and the derivative? More so, can you think of a rule or a formula besides the formal definition that connects the original to the derivative that works for every single one of these?
Is it a log?
What'd you say?
I said that the power is multiplied by the coefficient, and then one less than, or we don't have video when I joke.
All right, well, you said you multiplied the power by the coefficient, and then you do one less than the what? One less than the power, one less than the exponent. Well, let's see. What's the coefficient for x to the third?
1.
There's a 1. So if I multiply my exponent by my coefficient, don't I get 3?
Yes.
And then if I take away 1 from 3, don't I get 2? Okay, let's check it down here, okay? Because I already have a coefficient in front here. So I would multiply the exponent by the coefficient. What does that give me?
4.
And then if I take away 1 from the exponent, okay? Let's do this one, because this one has multiple pieces. What's the coefficient in front of this x squared? And then, so what's negative 1 times 2? Negative 2. Then I subtract 1. What's the exponent here on 5x? No, it's not 0, it's a 1. 1 times 5. When I subtract 1 from the exponent, that will give me x to what power? Anything to the 0 power is 1. So I'll give 5x to the 0 power, which just gives me 5. So that works out. But what happens with this -3?
Well, it doesn't have a well, it has a exponent of 1, so if you do 1 minus 1, it turns into a power of 0 and it turns into a 1 again.
Well, but if that's the case, wouldn't there be a 1 over here? Yeah. I think you're on it, but you said it doesn't have. Did you say something like it doesn't have a power?
No, it has power of 1.
But when we've been taking these exponents, all of them have come from variables, haven't they?
Yes.
If I wrote this 3 with the variable, this will be x to the what power? Then that would be 3.
0.
It's a 0. Constants can be written as the number times your variable to the 0 power, because anything to 0 power is 1. If I multiply the exponent to that coefficient, what happens? 0. Then there's nothing there. Okay? Let's look at this one here. Let's see, 3 times 2 is -1. Okay, so far so good. My question comes to this one though. So far the rule has worked. I mean, I didn't check these two, but I'm close to check almost all of them. What about this one? Can this rule still work with this one?
Isn't there like I think you had like a picture of all these rules and you can switch, you can turn that into another function with the same exact thing.
Yes, there was last year. I had put up a list of, they were rules, actually they were called laws,
Yeah.
that allowed you to take this, like 1 over x, and rewrite it. Who remembers what law we're talking about here? Who remembers? Or what's another way I could rewrite 1 over x?
X to the -1 power.
This can be rewritten as x to the -1 power. This is what came from your laws of exponents. Remember, anytime you had a variable in the denominator, you could flip it and make it a negative exponent. So now the rule, it still works. What's the coefficient in front?
1.
A 1. -1 times 1 is there's your -1. Then when I subtract 1, what does that become? So this becomes 1x to the -2. And you know we usually don't work with -1x to the -2, but we don't work with negative exponents. We make it positive to bring it back down. That right there, that is called the power rule. It's where you take the exponent, you multiply it by any coefficients in the front, and you subtract 1 from your exponent. Every time it's Anderson, every single time. So, rules for differentiation is what we're talking about here, okay? By going through that whole process on the other slide, you were able to see, just exactly how that rule connects. And like I said, that was called the power rule. But there are a few other different rules that are used to differentiate functions. I mean, we've kind of already talked about all of them when we went through and saw the connection between the original and the derivative of all the ones we've done so far using the formal definition. So, like I said, there are a number of rules that can be used to differentiate more complicated functions without using the formal definition. Because if we use the formal definition with some more complex ones, it's going to, like I said before, it's going to get very tedious. It's going to take a long time, and we could definitely make some mistakes along the way. However, it still can be done, but you want to use these other rules in those types of situations. So what we have here in this box are the different types of rules that we already talked about, but I just want to make sure that we have them. Your original function is a number, a constant, like 3 was, then the derivative of that is 0. And this is called differentiating a constant. So again, constants are just regular numbers, 3, -1, 2, et cetera, no variables. The derivative of any constant is 0. Now, when you have a power, okay, a variable raised to an exponent, the derivative of that is going to be the exponent times x, and then you subtract 1 from your exponent. So, for example, x to the third would be 3, because that's the value of n, x to the 3 minus 1, which is 2. And that's what we found using the formal definition. So that right there is called differentiating x to the n power. I do call it the power rule, because when you look online, other textbooks, that is like its name, okay? It's called the power rule. Let's say your function is c u of x. Now this c represents a constant and u of x represents some function. Let's say it is 2x to the third power. 2 represents your constant, x to the third represents your function. The derivative of something like this, where you have a constant times a function, you just multiply the constant by the derivative of the function. Since the constant's 2, and we already know that the derivative of x to the third is a 3x squared, then we just multiply the 2 constants together to get 6x squared, okay? So anytime there's a number in front of any power, any base to a power, you just multiply the exponent and that coefficient together and continue to subtract 1 from your exponent. And lastly, let's say you just have multiple functions added together to create one expression, such as that negative x squared plus 5x minus 3 from your homework. You are literally just taking the derivative of each individual piece separately, and you're just connecting them together to get the derivative, okay? That's called your addition rule. Yes, it does also work with subtraction as well, so don't let that throw you off. You'll just take the derivative of each individual piece. And these are your rules for finding the derivative instead of using the formal definition. This rule, the second one, is in your reference book, okay? This one's in your reference book, and really and truly, this is the main one. That second one is the main one compared to the other ones. So we're gonna use those rules now to find the derivative of each one of these functions, okay? So the first is y equals 5x to the third plus 6x squared minus 3x plus 2. Now for the very beginning, I'll show all the steps, you know, the multiplying and everything, but after today, I'm gonna just, you know, jump to what it is, okay? I just wanna make sure that everybody understands that. I wouldn't normally do everything I'm about to do on these problems. No, you don't, like, I mean, pretty sure. So, the derivative, remember, the derivative can be either written as a y prime or dy dx. Remember, these are different ways to indicate the derivative, okay? Let's apply our rules. Remember, we take the exponent, we're gonna multiply it to the coefficient. So that becomes 5 times 3, and then I need to subtract 1 from my exponent. So what is that?
15x squared.
15x squared is the first term. Now for the next term, I do the derivative of the next term. That's gonna be 6 times, remember I multiply the exponent to the coefficient, and then I subtract 1 from the exponent. What does that become? 12x. What's the exponent on this 3x? So 1. So I need to multiply it there as well. That's a -3. I'm going to multiply that by 1 and subtract 1 from my exponent. What does that become? It becomes a -3. Not a -3x because 1 minus 1 is 0. Anything to the 0 power is 1. So my variable is gone, but that constant's still there. And then what's the derivative of any constant? 0, always. So my derivative is 15x squared plus 12x minus 3. That is using the rules from the other page. Are there any questions?
No.
Now, if you look at the next one, you might be like, oh my goodness, I have fractions involved. But remember, your laws of exponents says that I can move that x out of the denominator to the numerator by doing what to it? Say again. Making it negative, and careful on the verbiage, not flipping it, but just bringing it up. So it'll be like this. Anytime you have variables in your denominator, you can bring them up to the numerator by making the exponent negative. So what would that be for this last term? How would I write that so it doesn't have any variables in my denominator? So let's find my derivative. Remember, the notation is f prime of x when it's written as f of x, okay? So what's the exponent here on the 7x?
1.
So I multiply. That's going to be 7. Do y'all get the hang of it?
Yes.
Do I need to show all these little steps in between? Okay. So I multiply 7 times 1, which is 7. Then I subtract 1 from the exponent. What will that give me? It'll just give me 7. Because technically it'd be x to the 0 power, which is just 7. Here, I have -1. I multiply that to -4. What does that give me? It gives me a positive 4. Then I need to subtract 1 from my exponent. What does that give me? -2. Can I have negative exponents? I can't have negative exponents, so I have to put the x and the square back on the bottom and make it positive. This one's -3. I multiply it by 3. What does that give me?
-9.
Then I subtract 1 from the exponent. That gives me a.
-4.
If I have negative exponents, I have to make it positive, so I bring that back down to the bottom. And that is my derivative, fully simplified. Right? Last but not least, this one over here. My suggestion would be to simplify it before you try to do anything crazy, because some of you may be thinking, oh, just bring it up, make it a negative x to -1, but now it's x to -1 times all of that. Remember, you can split up any numerator and divide it by its lone denominator like so. This, what I just wrote in black, is the same thing as the original function that's in print. What's x squared divided by x? X. What's 4x divided by x?
4.
And then this becomes just a -5 over x, but how can I rewrite it? It would be 5x to the -1 power. That is my original function, fully simplified. Now I can find the derivative, okay? So let's see. Prime of x, because we want to make sure we include the notation. Okay, so we know that we're talking about the derivative. What's the derivative of x?
1.
Very good. Because this exponent here is a 1. There's a coefficient of a 1, so you multiply. That'll basically give you 1x to the 0 power. Anything to the 0 power is 1. What's the derivative of 4? It's 0. Very good. And then this one over here, I multiply -1 to -5 to get a. And then I subtract 1 from the exponent to get a. But I cannot have a negative as an exponent, so then I bring just that variable to the bottom. And there's my derivative. You guys get that?
Yes.
All right. So now that we know the rules, instead of doing the formal definition, we can use these rules. Don't forget it. Keep it there, because if it ever asks you to show that the derivative is something, you use the formal definition to show that the derivative is what it is. Okay? But if it just asks you to find the derivative, then you use the rules. Such as this one. It says find the derivative of y equals x squared minus 4 over x, and hence find the gradient of the tangent to the function at the point where x equals 2. Two things you have to do here. You have to find the derivative, and then you have to find the gradient of the tangent. So let's start out by finding the derivative. I want you guys to do that because I want to make sure you guys are practicing with the rules. So find the derivative, and then we'll find the gradient of the tangent together. We found the derivative. What you get?
2x plus 4 over x squared.
We got 2x plus 4 over x squared. Very good. For those who didn't get it, just let's recap this. 2 times 1, that'll give you 2x. Then you subtract 1 there. Remember, this can be written as -4x to the -1. So you multiply -4 and -1 to get a positive 4, x to the -2. So yes, very good. Okay? So now that I have my derivative, this is the first part. Now it's asking for, hence, that means using your answer, find the gradient of the tangent to the function at the point where x equals 2. All that means, find the gradient of the tangent. And we know how to do that now that we have the derivative. What do I need to do? I plug in 2 to the x's. Now the proper notation to do this is technically this, okay? You don't necessarily have to write that, but that is the proper notation to indicate that I'm taking the derivative and I'm evaluating it when x is 2. Two times 2? 2 squared? So what is my gradient?
5.
Very good. And again, this is the gradient of my tangent line. Questions? All rows M subtangent.
We're not gonna have like units for this, right? Like,
Not for gradients, no.
so 5 is the gradient of the tangent.
For this particular graph, so whatever it looks like when x is 2, so however, I'm trying to remember what this function looks like. I don't know, it kind of looks, I think it kind of looks like this. I could be very wrong, okay? But basically when x is 2, that gradient line has a slope of 5. That's what that means. So the slope at that particular point is 5 because we base it off of the tangent line. Let's look at the next one. Okay, it's a little bit more involved. It says suppose f of x equals x squared plus b plus 1 x plus 2c. F of 2 is 4 and f prime of -1 is equal to 2. Find constants b and c. This is a little bit more on that IB level type of question here, okay? So let's just make sure you guys are aware of some things. This b plus 1 is a constant. It's some number. So whatever the value of b is, when you add 1 to it, you get the constant that goes with the x. And then 2c is, again, another constant. Once you figure out what c is, you multiply it by 2, you get the constant of this function. Now, f of 2 equals 4. You guys have seen this notation from Algebra 1, Algebra 2. Those took pre-cal, you saw it there as well. F is my original function. 2 represents what?
That what we put in for the x.
It's my x value. F of 2 is equal to 4. This 4 represents what? Y. So this is basically saying 2, 4 is a point on my original function. That's what this means. Fxn means function. Now over here, you have this notation. What does f prime mean? And we know that the derivative is associated with what? What about, more specifically? It represents the gradient of the tangent line. So again, -1 is in that x spot. And then f prime of -1 is equal to 2. This part here is saying at x equals -1, the gradient of the tangent line is equal to 2. That's what that means. So when you see that notation, that's what that's representing. I wanted to make sure to go over this because you will see this in the future, okay? So anytime you see f prime, that means you're talking about the slope of your tangent line at that particular point, in this case, x equals 1, and the slope is 2. So now that I have all that, let's find my constants, b and c, okay? So we can start out by, of course, finding the derivative. I'm going to find the derivative of each individual piece. Let's start with x squared. What's the derivative of x squared? 2x. Very good. Now over here, I have b plus 1x. Remember, b plus 1 is nothing but a constant. So this is a constant times x. What's the derivative of that?
0.
That'll be of the constant only. But like before, when you have 5x and I asked you to take the derivative of it, what was it? It's just 5. You just drop off that x. So if this is b plus 1, that represents a constant, times x, the derivative of that is just going to be b plus 1. Just the constant that's left over. Lastly, what's the derivative of any constant?
0.
0. So that 2c, the derivative of that 2c is just 0. So this is what you have to represent the derivative of f of x. Okay?
I have a question.
Uh-huh.
Wait, I'm lost.
So,
All right, hold on. Let me get Payne's question, then I got yours, Michaela.
so you put 0 into
No. 2c represents the constant of this function. So it's like what the -3 would be of this function. This right here is what 2c is for this problem. And the derivative of any constant is always 0. So this 0 right here represents the derivative of the 2c part of the function.
Since C is a number, like if you say it was 5 and then multiply by 2, that's going to be 10. If there's any number, it's going to be a constant, or just be 0. Yeah, but since it's finding a constant.
Right. Right, remember B and C, they're not variables here, they represent some numbers. So whatever those numbers are that we're about to find, we're gonna add 1 to B to get that number. It could be 4, so when I add it to 1, I get a 5x. Well, the derivative of 5x is just going to be 5. But I can assume that B is 5, I actually have to figure out what it is. Michaela, your question.
I'm confused on like everything after 2x. Like the derivative of b plus 1 is b plus 1.
No, the derivative of b plus 1x is b plus 1. It's the same thing as if you had 3x and you had to find the derivative of that, that would be just 3. The derivative of negative 4x, that would be just negative 4. The derivative of 5x, that would just be 5. This b plus 1, that is equivalent to those numbers that are in front of the x. So when you take the derivative of b plus 1x, you're just dropping off the x and left with that constant. The same thing that's happening here. All of these represent the original function. These are their respective derivatives. Every single time I'm left with just the number that's in front of the x. So when I take the derivative, I'm only left with the number that's in front of the x, which is that b plus 1 number.
And why is the derivative of bc 0?
You mean 2c?
I mean, yeah, 2c. Why is it 0?
Because c, again, is a constant. C could be 5. So if c is 5, that gives me 10. Well, the derivative of any constant is always 0. Collectively, 2c is a number, like negative 3, like 10, like 1. The derivative of any one of those numbers is always 0. So that's why a 0 is now there to represent the derivative of 2c.
So if b plus 1 didn't have the x, you would treat it with the constant rule, like it's 2c.
Exactly. Remember, b and c, they're not like what x is in the problem. They represent numbers. So I needed to figure out what my derivative was in order to be able to answer or to find the value of b. Now, since I know that the derivative when x is negative 1 is equal to 2, I can take my derivative, I can plug in negative 1 for x and set it equal to 2 to find the value of b. Questions on that?
No.
So I'm going to solve just this part right here. I'm going to solve for b. What's 2 times negative 1?
Negative 2.
Combine like terms, what's negative 2 plus 1?
Negative 1.
Then I need to solve for b by adding 1. So b is 3. B is that value of 3. So when I plug it in, that middle term is 4x. So I asked me for that, but I mean, that's what we would do. Actually, I didn't do that. I take that back. Oh, Jesus. Thank God I'm wearing black. All right. So right now, my function is x squared plus, if I plug in the value of b now, it's 4x. And now all I have left is to find the value of c. This is where I'm going to use this piece of information. Because if x is equal to 2, y should equal 4. So that means I can plug in 2 for x and set it equal to 4 because f of 2 should equal 4.
Why wouldn't you be able to use the derivative if it's part of -1?
Because I already used, well, actually I could, oh no, because the derivative no longer has any c. So I have to go back to the original. So now I want to solve this. What's 2 squared?
4.
Times 2. Combine like terms, 4 plus 8.
12.
Subtract 12 from both sides. Divide by 2. And there are your values of B and C. Again, still using the concept of the derivative rules and incorporating a few more items. Somebody online, give me what the derivative is. Or sorry, dy dx.
6x minus 4.
Say it again.
6x minus 4.
Very good. 6x minus 4. Remember, multiply, subtract 1, multiply, subtract 1. Okay? So yes, that is dy dx. What does that mean?
So this is the equation to find the gradient of x.
This is the equation to find. Say it again. To find the gradient of the tangent line at x, whatever x is. It could be any point along your function. I even add that in. On the function y. That's what you're doing every time you're finding the derivative. You basically are finding an equation or rule that will help you find the gradient, the slope of any tangent line at any x value on the original function. That's what that means. Here's another example. At what points on the curve of y equals 2x squared plus 5x minus 3 does the tangent have a gradient of 13? Tangent of the gradient of 13. That means the derivative is equal to 13. Because again, the derivative represents the slope or the gradient of the tangent line. We know that the slope is 13. So that means the first derivative has to equal 13. All right? Or in this case, let me use the proper notation. dy over dx, because it's y equals. So I need to find the derivative. I need to set it equal to 13, and I need to solve. What's the derivative of 2x squared?
4x plus 5.
And then of 5x is 5. I'm going to set the derivative equal to 13. I'm doing this because I'm trying to find the point now. So now instead of them giving me the x value to find the gradient, I'm now given the gradient, and now I have to find the x value. Actually, I have to find the full point. So now I'm going to solve for x by subtracting 5 from both sides, dividing both sides by 4, and x equals 2. So on this function, when x is 2, the slope of the tangent line is 13. But it's asking me for the point. I know the x, I have to plug it in to find the y. And where do I plug it into? The original. And again, I'm doing this because it's asking me to find the point where the gradient of the tangent line is 13. What'd you guys get?
215.
So the answer is 215. It's the point. At that point on this quadratic function, so this is a quadratic that points up. At the point 215, the gradient of the tangent line is what again? 13. That's what that means. And I'm just drawing this over here to the side so that way you guys are associating that with your mind, is that derivative means slope, the tangent line. Ooh. Here's another one similar to that number 5. It says the tangent to f of x equals 2x squared minus ax plus b at the point 2, 7 has a gradient of 3. Remember, tangent gradient indicates what? Say again? The derivative. So this part that I underlined in purple is saying that the derivative is equal to 3. So what's my derivative here?
X.
4x minus a. Very good. Because remember, a and b represent what? Constants. They represent numbers. So ax is like saying 4x. Ax is like saying negative 3x. So when I take the derivative of those, I get just that number that's associated, that's beside the x. And of course, the derivative of a constant is always 0. Okay? What's the value of x? A little louder. It's 2. Because if they gave me the point, that means that on this quadratic, at x equals 2, the gradient is 3. So I can even kind of clean this up a little bit and put a 2 in here. That will allow me to replace the x with the 2 and solve for a. And now that I know that a is 5, how can I find b? Plug a into the original equation. Plug in what? I can plug in the x and y of the point that was given to me. I can plug in 7 for my y and 2 for my x to find the value of b. 2 squared times 2, negative 5 times 2. What's 8 minus 10? What's the value of b? And that's how you can use the rules of derivatives or rules of differentiation to find the derivative, a lot easier than using the formal definition. Also, how I can find gradients of tangent lines using the rules. Even how to find points, like we did in number 7, how to find points where the gradients of particular value, or even how to find actual expressions, actual functions, knowing this information.